Hello again. We have another video lecture. This is video lecture 7.2. It corresponds to the reading in our book, Chapter 7, Section 3, which is about work done by the gravitational force. We've learned in video lecture 7.1, both parts of it, that forces do work on particles. We introduced this new concept of work and how to calculate work done by a force. To be more specific, work done by what is called a constant force acting on a particle, meaning the force doesn't change in either magnitude or direction as the particle moves. Well, the gravitational force is a constant force. F-grav always points in the same direction, vertically down, and it always has magnitude m times little g. No matter what kind of motion the particle is experiencing. So yeah, F-grav is a constant force, so we ought to be able to calculate the work done on a particle by the gravitational force. It's got to be a particle that's moving, because remember, to have work done by a constant force, you need a displacement. Your particle must move. Okay. So let's talk about how we're going to calculate work done by gravitational force. It's going to be one of the most important work calculations we do. Okay? Work done by the gravitational force. Let's just take a specific scenario so that we can be clear visualizing what we're going to imagine. Let's take a projectile of some mass m. Maybe it's a soccer ball, or I suppose as the rest of the world calls it, a football. Soccer ball that we're going to kick starting from the ground, and all we do with our foot to give it the kick in kicking it is give it an initial velocity. After that, we don't touch it. We're going to ignore air resistance, and so the only force acting is F-grav, and the soccer ball will fly through the air along a parabolic trajectory. Projectile motion, chapter 4. How do we calculate the work done by F-grav in such a motion? So first, what I've got here is a static picture in the lower left area of the screen with a horizontal x-axis in meters along the ground and a vertical y-axis in meters. And actually, with the given distances here, probably wouldn't be a soccer ball because the distances are too large. But whatever it is, it's some kind of projectile, and it's undergoing projectile motion. Its actual trajectory from the point it started at the origin is this purple curved path right here, which of course we know is a parabola. Now, there it is right there. There's the projectile. What we did in making this drawing is we said, freeze, take a snapshot, and that's where it was in its parabolic trajectory. Of course, as time goes on, it continues along its parabolic path until that projectile reaches the ground. But what I've done in my drawing here is I just said freeze. Okay? Let's take a snapshot and let's look at what's happened from the beginning of the motion down there at the origin up to where it is right now. Okay? How much work has the gravitational force done on this particle from the starting point to this point? That's my question. Okay? As I write here, we are interested in calculating the work done on the particle by the gravitational force between firing and arbitrary instant during flight, which I've just drawn there, an arbitrary instant. So I'm going to take us through the calculation. It's actually no new physics. It's the physics of the previous video lectures. That is to say, calculating work done by a constant force. Here we go. Work done by a constant force, in this case gravitational force, so I label it W-grav, or sometimes I'll label it just W-g. I think you get the idea. W-grav is F-grav dot delta R. Right? Scalar product of the force, F-grav, and the displacement. Let's make sure we're clear on those two vectors. They're drawn in the picture. Notice the F-grav. There it is with its tail anchored on the particle, and it points vertically down. It's labeled right there, F-grav. Of course it points vertically down. The other important vector in the work calculation is delta r, the displacement, from the starting point at the origin to the point where we are. And that's the delta r, the displacement, points in a straight line from the starting point to the ending point. So that's the delta r. Okay? That's what we have to use in the scalar product to calculate W grav. So F grav dot delta r, and both those vectors, F grav and delta r, must be clearly drawn as they are here. Next step is to use the definition of scalar product. Previous video lecture. For the scalar product of any two vectors, you take the magnitude of the first vector times the magnitude of the second vector times the cosine of phi, where phi represents the angle between those vectors when they're drawn with a common tail. Now, in my drawing, the F grav and the delta r are not drawn with a common tail. But let's make them have a common tail. All we got to do, all I'm going to do, is slide the delta r rigidly straight out along the same direction until its tail coincides with F grav. I'll sketch it. It would go out along this way. Like that. Right? I just extended. I slid the delta r. Okay? So that its tail coincides with F grav. Now I see why the angle marked with the red arc is labeled with a phi, because that's the phi that goes in cosine phi. You understand that? That has to be very clear, because we can't set up this whole formalism of scalar products and tell everybody exactly how to calculate a scalar product and then turn right around and do something else. Okay? Scalar product says take the magnitude of the first vector times the magnitude of the second vector times the cosine of the angle between those vectors when they're drawn with a common tail. So that's the angle phi that you see right there. And that's what we have to take the cosine of. Okay, let's go on to the next line in the calculation of W grav. All right, first thing you see is mg on the right. That's the magnitude of F grav, yes? Then you see I've denoted magnitude delta r. Now I'm going to work with the angle phi a bit. All right, now I'm going to need to clear out a little bit, give myself some space here. It's going to be convenient, for reasons I hope will be clear in just a moment, to write the angle phi as follows. I'm going to break up that angle phi that you see into two parts. Let me draw a horizontal line going straight across. That right there is a right angle, 90 degrees. And then what I have, just extend that a little bit, is another bit right there. I'm going to label that angle alpha. That's a Greek letter alpha. So all I've done is to say that the angle phi is equal to 90 degrees plus the angle that I've marked as alpha. All right, that's just geometry. But note that that angle that I've marked as alpha is the same as the angle alpha marked down here, which is the angle that delta r vector makes with the origin right down here at the lower left. It's the same alpha from geometry. That's going to be important. But for now, all I've done in the work calculation is replace phi with 90 degrees plus alpha. All right, here's the next thing I'm going to do. I'm going to remind you of a trig identity that, if you had a good trig teacher in high school, you were taught, even if you don't remember it now. And that was this, that the cosine of 90 degrees plus an angle, in this case we'll denote it as alpha, is equal to the negative sine of the angle alpha. That comes from the trig identity for the cosine of the sum of two angles. Cosine of the sum of two angles is cosine of the first angle times the cosine of the second angle minus the sine of the first angle times the sine of the second angle. When you apply that to 90 degrees and alpha, you end up with minus sine alpha. So that's the next line in the work grav calculation. Minus sine alpha with mg times the magnitude of delta r. Okay, now here comes the next really important thing from this picture. Magnitude delta r sine alpha. I want to interpret that. Just that part. I'll write it over here. Magnitude delta r times sine alpha. I want you to look at this right triangle down here, made by delta r, and that vertical side and that horizontal side, right there. That right triangle. Right angle, right there. Magnitude of delta r is the hypotenuse of that right triangle. So magnitude delta r sine alpha, that's just the length of the side opposite to alpha, and that's just the length that has been labeled in the picture delta y. Because that height is just the change in the y-coordinate of the particle between the starting point and that point. Do you see that? Magnitude r sine alpha is just delta y, the change in the y-coordinate. So we end up with the formula that I'm going to use to calculate the work done by gravitational force. It's a nice handy formula for calculating W grav. It is based on an assumption over here of a plus y-axis pointing up, vertically up, and the formula is W grav is minus m times g times the change in the y-coordinate. And I don't recommend you call it anything else. Don't call it height or change in height. It's the change in the y-coordinate between the starting point and the ending point. Okay? That's what we're going to use. It's very handy. Okay? Just use that formula for calculating W grav. But remember, the delta y is based on an assumption of a y-axis pointing vertically up. So let me show you a Wiley plus animation of a situation like this, where a projectile is fired, given an initial velocity. It then undergoes a parabolic trajectory of projectile motion. Okay? And we're going to ask how much work is done by gravity between the starting point and whatever point we pick. Okay, so there's the x and y axes. There's the particle there at the origin. We're going to run the animation, and that's going to get it moving. And I'm going to run it first, and then I'm going to bring it back and talk about it some more. So first, let's just watch it move. There'll be a lot of vectors you'll see. Let's just watch. Of course, that's just a parabolic trajectory. It goes up, and it comes down, and it lands on the ground. Okay? Now let me drag it back a bit. Oh, how about like that? Because that's roughly like the static picture I just showed you, isn't it? There's the displacement delta r from the starting point out to where it currently is. There's F grav downward. There's the angle phi, and delta y is the change in the y-coordinate. So if I asked you to calculate W grav, or how about this? Let's just try this. We'll just do an estimate here, okay? Let's just do an estimate. Let me try to get lined up the projectile so that it's lined up roughly with a y-coordinate of 50 meters. Then the delta y is 50 meters. It says down there in the wording that the m is 2 kilograms. Let's take g to be 10, just to have a nice simple number, meters per second squared, or 10 Newton per kilogram. So the work done by gravity would be negative mg delta y. Don't forget that negative. So negative 2 times 10 is 20, times delta y is 50. So is that 1,000, right? 20 times 50 is negative 1,000 Newton times meter. If I click this button here that says show plot, all right, it's going to show me the actual value of W grav. I was close, negative 1,011. Well, I did just approximate. There, I'm pretty close. Pretty close, okay? Now that's the W grav between the starting point and that point. Of course, the value of the W grav depends on when you decide to look. Maybe you'd ask about, hey, what's W grav between the starting point and the high point? then you'd have to use the delta y between the starting point and the high point and calculate the W graph. The graph shows you that it's about negative 1250 Newton times meter. Note negative, because the delta y is positive, but there's a negative sign out front in W graph. If I asked you, what's W grav between the firing point and the landing point, notice what you should say. You should say 0. Because even though it moved, its delta y for that trip is 0. Yes? It started and ended at the same y value. So the net W grav in that case is 0. We got to stick to the formulas and interpret them correctly. All right, let's go back and do more pictures and do some more practice with W grav. Okay? All right, here we go. Next picture. Practice. Work done by gravitational force. In the figure below, we have a greased pig, and it has a choice of 3 frictionless slides along which to slide to the ground. Slide A, slide B, slide C. We are to rank the 3 slides, A, B, C, according to how much work the gravitational force does on the pig during the descent. Greatest first. Now, to help us think about that, let me say that the vertical height between the starting level of the pig and the ending level of the pig is just some amount h. All right, so I'm going to let you think about that. You could pause the video, rank the W values, W grav, for slide A, B, and C, biggest to smallest. Okay, pause the video. Okay, what did you say for the ranking of the W's? W grav for the 3 slides. Let's figure it out. Why don't we do that? Right? That's what I would ask you to do if it were on a quiz or an exam. You have to justify your work. I'm going to label it WG. Let's use that new formula we just derived. Negative mg delta y. Let's use it correctly. Okay? Well, it's the same pig, right? So in all 3 cases, it's the same m. All these experiments are done on Earth, so in all 3 cases, it's the same g, whether this pig goes down slide A, or slide B, or slide C. So it's all going to boil down to how the delta y's compare. You know, because it's not immediately clear, because the slides have rather different shapes. Slide A is very steep. Slide C is kind of shallow going down, and slide B is in between. So you might think that the shape of the slide is important. But notice something. For all 3 slides, is not the delta y the same? What is the delta y for all 3 slides? Think about that a second. Get an answer in your head, but be careful. Did you say that delta y equals negative h for all 3 slides? And the negative sign is vital, because this formula up here for W grav is derived assuming a y-axis going vertically up. And this pig goes from a point with a y-coordinate up here to a point with a y-coordinate on the ground. And in all 3 cases, that's a downward motion, so the delta y is negative, and of course it's negative h. So that means my formula for W grav is negative mg multiplied by negative h, which is positive mgh. Gravitational force does positive work, and it does the same amount of work in all 3 cases. Yes? So the ranking is W grav for slide A equals W grav for slide B equals W grav for slide C. They tie. Okay? To calculate the work done by gravity, I don't care about the details of your path. I just need to know what your delta y was. Now here's another question. It's like the one that I showed at the very beginning of video lecture 7.1 with the child going down the water slide to motivate the whole point of introducing some new physics, namely work and kinetic energy. But here's what I'd like to rank now. the final speed of the pig. The speed of the pig at the bottom of the slide in the three cases. How do those speed values rank for slides A, B, and C? Now maybe the shape of the slide is important. I'm going to let you think about that. You're welcome to pause the video and then come back. Okay, so how are we going to determine the speed of the pig at the base of each slide? Well, I will tell you, like I did when I talked about the water slide. If you try to answer that question using Newton's second law, it's going to be hard, and the shape of the slide then comes into play. But if we use our new ideas, namely the work kinetic energy theorem, the answer will come out very easily. Okay? So we're going to use, to rank the speeds, what's called the work kinetic energy theorem. That was previous video lecture. W net equals change in kinetic energy. All right. Now, where? Let's write down what we can about W net. You got to start from that, and that means the net work done on the pig by all forces acting on the pig. Okay, it says it's a grease pig. That's code for ignore friction. So how many forces are acting on the pig during any part of the slide? Don't worry about some complication like the pig loses contact with the slide or something. Don't worry about that. Well, let's just imagine kind of coming down, let's say that straighter slide, slide C like that. Aren't there two forces? Good old F grav, vertically down, and a normal force, perpendicular to the surface, no friction. So there are two forces. So W net would in principle have two contributions, the work done by the normal force and the work done by the gravitational force. Okay? All right. Next thing to note is that the work done by the normal force is zero. How do I know that? It's easiest to see with slide C. The normal force is perpendicular to the slide, but the displacement is along the slide, like that purple arrow. That's the direction of the delta R, and that's a right angle between them. So when I do F normal dot delta R, I'm going to end up taking the cosine of 90 degrees, and the cosine of 90 degrees is zero. The normal force does no work. And that's true even on those that curved slide like A. Now that's not so easy to imagine. You have to do a little bit more subtle thinking there. The trick is to just imagine the motion along any of the slides, including A, as a whole bunch of little infinitesimal displacements, one after the other. And for each little infinitesimal displacement, the dr is along the slide, but the F normal is perpendicular to the slide. So you're always going to take the dot product of perpendicular vectors. The normal force basically is not going to do any work in a situation like this. So the only force doing work is W grav. But we already ranked those, didn't we? They're all equal for all three slides. That's important. So now let's go back and think about delta K, the change in the kinetic energy. Well, that means K at point 2, the ending point, minus K at point 1. Point 2 is down here at the bottom of the slide. Doesn't matter which one. And point 1's at the top. I'm assuming that the pig starts from rest, so K1 is 0. And for K2, I'll just write 1/2 m v2 squared. And it's that v2 that I'm asking to rank for the three slides. How do the v's compare at the base of the slides? So you put these results together. W net equals delta K. W net is W grav. And delta K is 1/2 m v final squared. So now let's just solve for v final. V final is the square root of 2 times W grav over m. But we just ranked the W grav and they're all equal. So the final speed is the same in all three cases. Doesn't matter whether the pig goes down the long slide, slide C, or the steep slide, slide A. The pig will end up with the same final speed. What will be different in those cases, though, is the amount of time it takes the pig to get down. but we won't worry about that. Okay, let me talk about one more topic in this discussion of work done by gravitational force, because it comes up pretty often. It's a somewhat handy thing to calculate, but it's just a little subtle if you don't see all the parts of the argument laid out before you, at least once. It's asking about the work done by us, or maybe machinery, in raising or lowering an object. So here's the situation I want us to imagine. Let's say we take an orange of mass m, and we're going to lift it from the floor to a table of height h. So let me start. I'm going to be sketching it here. There's the floor. And I don't really have an orange pen. No, but I'll use red. So it's a red orange. Okay? There's the orange. Starts out at point 1 here on the floor. Let me draw a table. You don't have to be an artist here. That's the table. 4 legs and a top. Let's say it's, well, we know its height is h. And we're going to take the orange from point 1, and we're going to lift it, right? We're just going to pick it up in our hand and lift it and carry it and put it on the top of the table. And I don't really even care about how exactly I move it. Maybe I just bring it along a little bit of a curved path until I bring the orange at point 2 up onto the top of the table. Okay? Simple scenario. Here's what I want to think about. We're going to apply the work kinetic energy theorem to the orange. We're going to assume that it starts and stops from rest. I mean, it's initially at rest here on the floor, so V1 is 0. And when I release it there at point 2, I'm going to leave it at rest, so V2 is 0. So assuming it starts and stops from rest, I want to solve for the work done by my applied force. Okay? All right, so let's just imagine at some intermediate point along this path when I'm moving the orange, and let's think about the forces. Don't overcomplicate it. There's, of course, F grav, vertically down, and then there's the force from my hand, and nothing else is touching the orange, right? Now, I don't know exactly what direction or magnitude my hand force has. I'll just call it an applied force. But it's probably some direction roughly like that. The beauty of this calculation is I don't need to know the details of my applied force to calculate the work the applied force does. In this case, I'm going to show you how. All right? And that applied force doesn't even have to be constant. In fact, it probably can't be. I'm probably going to have to adjust my applied force to get the orange to move along this trajectory and then leave it at rest at point 2. But my applied force is going to be very complicated. Definitely not constant. Yet I want to calculate the work done by my applied force. Seems like a hopeless job. We're saved by 2 things. The assumption that the orange starts and stops from rest, or at rest, and that the other force acting on the orange, F grav, is constant. So here we go. Now it tells us what key physics to use, the work kinetic energy theorem, for the orange. So W net equals the change in the kinetic energy, delta K. All right, let's write down each side. Well, there are 2 forces, right, acting on the orange. My applied force, so there's the work done by my applied force, W applied, plus the work done by the gravitational force, WG. That's the symbolic way to write W net. Then, delta K. Well, that means the kinetic energy at point 2 minus the kinetic energy at point 1. Oh, but wait. It starts at rest, so K1 is 0, and it ends up at rest, so K2 is 0. So delta K is 0 minus 0. Even if in between the kinetic energy wasn't 0. I don't care. I only need K2, K final, minus K1, K initial. They're both 0. So W net must equal 0. So W applied plus W gravitational must equal 0. So my applied work at the end of all this is just the negative of the work done by gravity, even though my applied force isn't constant. No matter how complicated my applied force is, if the orange starts and stops at rest, then my applied work is just the negative of the work done by gravity. And that's an easy way to get W applied. Now, we have a formula for W grav. Let's use it. So that's negative, and here's the formula for W grav. Negative mg delta y. Don't do this too fast. Got two negatives multiplied together. So that's positive mg delta y, and delta y is positive h, so it's just simply mgh, positive. And that's how much work I must do with my applied force. Take the mass of the orange times g times that h, the height of the table. And it doesn't matter whether I do this lifting of the orange slowly or rapidly. The orange starts from rest and ends at rest. The amount of work I do is m times g times h. Okay? Now that's a very handy thing to remember for calculating work done by applied force. When they ask you for that, they're almost always going to be asking you in a situation where the particle starts and stops at rest. Okay, that's all I'm going to say for now about W grav. We'll be using it, we'll be calculating it a lot in chapter 7 and 8. But that's all for this video.